Hello everyone, welcome to our first asynchronous YouTube modern physics lecture. Okay, so you saw the intro video that I posted for both of my classes, so that was also the intro for my 206. It takes me half a day to upload each video, so I'm trying to reuse videos when I can, so you guys don't get your own personalized intro other than this. So before we do anything, really, maybe it's useful for you to just pause this video and go back and look over your notes from the past couple classes. Okay, so what we're going to do is we're going to go over a couple questions from the exam that some people seem to have problems with, and then we're going to get started with our regular lecture. Okay, so here is key for the exam, right? And I want to go over a couple problems from it. So the first one is this problem number 3, right? And this question asks, an electron is confined to a wire of length 0.3 millimeters. If the mass of an electron is 9 times 10 to the 31 kilograms, what is the uncertainty of the electron speed? So this is a question about the Heisenberg uncertainty principle, right? That we can't absolutely define the position or momentum of a particle, and the more we define one, the less defined we make the other. So we start off with the typical Heisenberg uncertainty relation, delta x, delta p, greater than or equal to h bar over 2. Okay, so this is essentially a little plug and chug with a couple steps. But there's a little trick to it, which is, of course, you have to realize that the little segment of the wire, that's going to be our delta x, because that's the area that we know the electron is confined to, right? And then the next thing is going to be the delta p, and what the question is asking for is the uncertainty in the electron speed. So we know that momentum is mass times velocity, so we plug that in, and we get 0.003 blah, 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 delta V equals some other numbers, and the rest is just a couple lines of algebra. Okay, I'm not going to go over number 4, but if you want to see how it works, just pause it and, go through the math. The other one I wanted to go through was number 5, which a particle has a wave function in the form psi equals x squared, but defined only in the interval 0 to 2. Do the following. Normalize the function, find the expectation value of the x operator, the expectation value of the p operator, and find the probability that the particle is located in the interval of 0 to 1. So in that first half of the wave function. So first of all, this is not a real wave function. It wouldn't work if you tried to write it down in a real theory, right, for a few reasons. Only some functions are solutions to the Schrodinger wave equation. X squared is not one of those functions, right? But there are only a few wave functions that are sort of tractable at this level, so I just made up a little function so you could go through the math, right? When, of course, you get to your real quantum mechanics, you'll be working with real functions which are more complicated and require a bit more of calculus and differential knowledge and stuff like that. Okay, so the first thing we want to do is normalize the function. So that's what we want to do to any quantum wave function when we first look at it, right? We have to make sure it's normalized, or else everything else is going to be wrong, essentially. Right? So the way we do that is we integrate over the wave function multiplied with its own complex conjugate. So since x squared has no imaginary components, I'm just multiplying x squared times x squared, and I get x to the 4th. And then integrate that over the entire interval over which the function exists. So for here, that's just 0 to 2. Now, if I wanted to be absolutely technically correct, I could do this integration from negative infinity to positive infinity, but then I would have to define my wave function as a piecewise function that's only defined from 0 to 2. So it's exactly the same thing, and this is just way easier. So that's, what we're going to do. And then the bit that you need to have some knowledge about is that in order to normalize a wave function, we multiply that wave function by some constant, and then we carry through this integral, and we set it equal to 1. So whatever this absolute value squared c is, that's going to be our normalization factor. So we just do this integral. It's fairly direct. And we get this guy over here. We flip it around because now we have c squared 32 over 5 equal to 1. and then we get our normalization constant. So this is what sits out front of the wave function when we calculate things, right? And then, I mean, I've skipped some steps, but if I want to calculate the x expectation value of this wave function, I put in an x, right, in there essentially. So I get another x, I get x to the 5, and then of course I do the integral, I get x to the 6, and I do this, right? And that means that the most likely position of this object that has that x squared wave function is going to be 10 over 6, so a little bit more than, or a little bit less than 2, right? So it's going to be, of course, much more likely to be where the wave function itself is largest. Okay. The next one is the p expectation value. So again, we just stick that operator between the two wave functions. Right? Our normalization is out front here. And this negative I h bar d by dx, right? I go through that, it's fairly straightforward, and I get this weird number, right? Which is not a real number, and this is why you can, or rather how you can see that this is not a real wave function, because I get a nonsensical imaginary answer. So I'm pretty sure I mentioned that during the test, that since this wasn't a real wave function, you didn't have to worry about getting weird imaginary results. Okay. So the next thing is to calculate the probability that it's between 0 and 1. So I just carry over that same integral, right, that I did up here, but with the normalization, of course, and now just from 0 to 1. And that tells you the probability that that particle is in that first half of that segment, right, of the x-axis. And I just get 1 over 32, right, because it's quite unlikely that the particle is going to be there because, of course, this x squared function, right, looks something like this. And if I'm drawing this in half, obviously it's much less likely it's going to be over here compared to over here. Okay, so that's all I really wanted to go over the exam. If you have some questions about it, you can email me. For my other class, I set up a online forum on Reddit, if you're familiar with that website. I might do that for this class if you guys want, or else you could just perhaps email me and I could answer your questions in the next video. We can kind of feel that out and see how that would work. If you want to look at all of the tests, right, I'll just put it here and then I'll flip through it and then you can pause if you want to see particular bits of it, right? And I guess that's it. Okay. All right, so let's get started with today's lecture. So today's going to be lecture number 14. We're on chapter 8. I'm going to cover stuff that's on pages 338 to 353. For next class, read 354 to 364. Homework, who knows what's going to happen with homework. I'll figure that out soon. Obviously, you may have noticed I haven't been super great about staying up on getting your homework back to you this semester, and now there's going to be more problems, unfortunately. But hopefully you can bear with me, and I'll get you some homework assignments pretty soon and figure out how I'm going to give you feedback and grade them, etc. Okay. So today we're going to go over more classical statistics. Right, and cement our knowledge of that before we get into intro to quantum statistics. Okay. So the last time we saw each other, we talked a lot about these different functions you can use to calculate statistics for classical systems. So we found the distribution of energies, of velocities, etc., etc. So one more example I want to go through is finding the distribution for kinetic energies of a gas. So in order to do that, we write down this guy here, which this is just going to be you know, this is our distribution and this is the infinitesimal energy. So we're going to write explicitly our distribution in terms of the energy. And what this guy means is the number of particles or elements of a system that have a particular energy between n argument some energy to n, I'll just write it. So this would be the number of particles that have a particular energy between these 2 points, essentially. Right, so if this is some E naught. Right, so this is just an infinitesimal slice of this energy distribution, essentially. Right, so just to be clear, this like